Welcome to Chapter 2, Reasoning and Proof for Geometry. So obviously all of Chapter 2 is looking at those two concepts, the idea of reasoning and the idea of proof or proving statements. So today's lesson, 2.1, is the idea of using inductive reasoning. So the goal for today is to describe patterns and be able to use inductive reasoning. In mathematics, you'll see that we typically have two types of reasoning that are our main approaches. We have inductive reasoning and deductive reasoning. So today we're just looking at inductive. Now, inductive reasoning we'll define in a little bit, but it has to deal with looking at patterns and making predictions or conclusions based on those patterns. So in example 1, they give us the first 3 figures in a pattern, and they ask us to sketch the next figure in a pattern. So what I notice is the shaded region is moving clockwise each time. So for our fourth drawing, the bottom right section would be shaded, and the pattern is that the shaded thing is moving one spot counterclockwise. In B, looking at the pattern, the first image doesn't give me a lot until I look at the next 2. What I notice is they are adding a dot to each side of this triangle made of dots. So the first time, each side was 2. Next time, each side had 3 dots. Next time, each side had 4 dots. So our next one in the pattern would have 5 dots on each side of the triangle. Example 2, again, is looking at patterns, and they're asking, based on these first few drawings, how many squares are there in the next object? So our first 4 are drawn, or you'll have to draw them, but the first 4 are these. So our first one is just a single box. Next one is 3, kind of in the shape of an L. Next one are 6, and the next one has 10 boxes or squares. So I'm looking for the pattern each time I go. So from the first drawing to the next drawing, I added 2 squares. From the second to the third, I added 3. From the third to the fourth, I added 4. So each time that I'm doing a new figure, I'm adding 1 more square than the step before. So step 4 has 10 squares. To get to step 5, we're adding 5 more. And in that case, it would be 15 for the next drawing. So how many squares would there be in the next object? It would be 15. Example 3, describe a pattern in numbers. Write the next number in the pattern. So if we're describing a pattern in numbers, we're saying something like increasing by blank, multiplied by blank, decreased by blank. And then to say the next number in the sequence, we would just look at where they ended and follow the pattern for the next one. So in A, they gave us the list 5, 10, 15, 20. So they are increasing by 5 each time, meaning the next number in the pattern would be 25. At B, we have 2, 6, 18, 54. So what's happening each time is they're multiplying by 3. 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54. 54 times 3 will give us our next number of 162. In C, our list starts at 26, then 23, 20, 17. So each time, describing the pattern, they're decreasing by 3. So our next number would be a 14. In D, the list goes 3, -9, +27, -81. So in this case, our pattern each time is multiplying by a -3. So -81 multiplied by -3 gives me a +240. And the last one in that list, example E, 64, 32, 16, 8. So each time they are dividing by 2, which means the next number would be a 4. So first page notes here is simply looking at patterns and describing or answering what would come next. Then we get into these two definitions. The first definition that we have is the definition of a conjecture. So a conjecture is an unproven statement that is based on observations. So remember, to prove a statement, we need to prove that it's true in all situations. A conjecture isn't fully proven, but it's based on observations. And then we have inductive reasoning, which is the whole foundation of this lesson. And inductive reasoning can be simplified or defined as when you find a pattern in specific cases, and then you write a conjecture for the rule of that pattern. So looking here, my conjecture for pattern A is that they're increasing by 5. I haven't proven that for every number in the list going on forever, but looking at my observations, they've been increasing by 5. So that would be my conjecture and my general rule. So in example 4, they ask us to complete the conjecture based on the pattern you observe in the specific cases. So we're going to be completing the conjecture. So it says in part A, use the following products meaning multiplication, of odd integers. Remember, integers are positive or negative whole numbers or 0, to complete the conjecture about the product of any two odd numbers. So if I'm looking at what they give me, 1 times 3 is 3, 1 times 5 is 5, 3 times 3 is 9, 3 times 5 is 15, and so on. I even added a few of my own examples. 7 times 9 is 63. 9 times 11 is 99. So what I'm noticing is every time that I'm finding the product of odd integers, my final product is also an odd value. Every answer that they've gotten so far was an odd. So the conjecture for that scenario is that the product of any two odd integers is an odd value. So based on what they gave me as examples, two odds give me the product, which is also odd. In B, it says complete the table and then complete the conjecture. So the table didn't print very well, but we'll pretend there's a line going across here. On top is the pair of odd numbers. In the middle would be the sum of the numbers divided by 2. And the bottom row of our table would be the average of those numbers. So if we're given the pair 1 and 3, the sum of the numbers divided by 2 is 1 plus 3 over 2, which gives us the average of 2. Same with the 3 comma 5. The sum divided by 2, 3 plus 5 over 2, gives us the average of 4. 5 plus 7 over 2. 12 divided by 2 gives us the average of 6. Do the same with 7 and 9, the same with the 9 and 11. So we've completed the table based on the info they gave us. So our conjecture based on this information is that the average of any two consecutive odd numbers is always going to give us an even value because all of our averages became even. So then our final idea for today is the idea of a counterexample. Now a counterexample is a situation that proves a statement or conjecture is false. So it's a situation in which the conjecture statement is false. Now, in order to prove something's true in geometry, we have to prove it for all situations. In order to prove something is false, we only need one counterexample. So in example 5, it says, show the conjecture is false by finding the counterexample. So in A, the average of any two consecutive even numbers is an even number. So consecutive even numbers would be like 2 and 4, 4 and 6, 6 and 8, so on. So if I find the average of 4 and 6, 4 plus 6 divided by 2, add the two numbers and divide by 2 to get the average, gives me 5. There's my counterexample. I ended up with an odd number, not an even number, so this is a counterexample to that conjecture. Same with 10 and 12, 10 plus 12 is 22, 22 divided by 2 is 11. So either one of these is a counterexample. In B, they're saying any four-sided polygon is a square. Well, we have plenty of four-sided figures that are not squares. We have rhombuses, we have rectangles, we have trapezoids. So you could draw any four-sided figure, like this one or this one, that is not a square, and that's your counterexample. And then in C, it says the square of any integer is a positive integer. Well, we know any negative squared is always a positive. We also know any positive squared is also a positive. So far it sounds like this conjecture is true. Except 0 is an integer. 0 is neither positive or negative. So when we do 0 squared, we end up with 0. So our counterexample to this statement, the square of any integer is a positive integer, is false because 0 squared is 0. Now you can ignore the problem numbers in the bottom right corner there. Those are actually not the correct ones for your class this year. So ignore those there, don't worry about that, and look in Google Classroom or on the course schedule for the correct problem page numbers. But the key idea for today, and the idea behind inductive reasoning, is that inductive reasoning is based on that idea of patterns and can be simply defined as when you find a pattern in a specific case, and then you write a conjecture for the general rule.